Good morning, ma'am. Am I audible, ma'am? Screen visible?
Yes, sir.
Yes,
Yeah, okay. Thank you. Thank you. 19 members are there. We'll start. Let the people join. Already it is delayed. So as last class, we are discussing about this constant volume batch reactor and other things. So we'll have one more important topic, that is your rate you can write in terms of Ni, that is number of moles disappeared, or even the concentration, right? We can write a rate Ni in terms of pressures also, especially if there is a gas phase reactions, we have to write in terms of pressure, because most gas phase reactions, your volume will increase or decrease. So there will be a change in volume. So we have to write in terms of the pressure also. So we'll see today that, right? So this is the same Levenspel book. So you can see here for a constant density process, especially if there is a liquid phase reaction, density will be constant generally, because you cannot compress the liquid. For a constant density process, you can call it as a constant volume batch reactor. You can write RI as 1 by V dNi by dt, since the volume of the reactor is constant because it is a constant density process. You are taking the volume inside the Ni to give you Ni by V is Ci. This is what we till now discussed. But if there is a gas phase reactions, you can write your C, that is concentration for ideal gas, as P by RT. P is the pressure, R is the gas constant, T is the temperature, absolute temperature. So R and T is constant because T is also constant temperature. If you write C as P by RT and Ca as Pi by RT, since 1 by RT is constant, I am taking outside, I can write my appearance or disappearance as Ri is 1 by RT dPi by dt. So you can write rate in terms of three quantities. One is number of moles, and then concentration, otherwise in terms of pressures. This pressures, it will be very useful when we are writing the gas phase reactions. Unless if it is your reaction is liquid phase, we just use these two expressions, right? Now when there is a pressure you are writing, especially in terms of a gas phase reactions, if the gas contains a mixture of gases, then you have to write the partial pressure of a particular component to that of the total pressure. That we can do now. Thus, the rate of a reaction of any component is given by the rate of change of its concentration or partial pressure, right? If there is a gas, Pi is the partial pressure. Now here, if when there is a gas phase reactions and when there is a number of change in moles or change in volume, then how to write this particular rate, right? For a gas reactions with changing number of moles, a simple way of finding the reaction rate is to follow the change in the total pressure, pi. So of the system you are having gas of different concentrations or gives different partial pressures, the total pressure is nothing but the sum of all the pressures of the gas which is excited. So that let it be pi. So if you can write in terms of the total pressure, then it will be simple. How to write in terms of the total pressure, we'll see now. So analysis of total pressure data obtained in a constant volume system. The volume of the system is constant. Now how to get the total pressure data? Yeah, here, right? So I'll just read here and then we'll do the derivation here. For isothermal gas reactions where the number of moles of material changes during the reaction, let us develop the general expression which relates the changing total pressure. Changing total pressure is nothing but pi to the change in concentration or partial pressure of any reaction component. So I am assuming my mixture is having some different amount of different gases A, B, C, D, E. So when there are that particular some different gases, how can I write this total pressure with respect to the change in concentration? That is what we will do. Let us assume your reaction is AA plus BB plus still a lot of elements are there, gives RR, ESS, like that till a lot of products you are getting. So small a is the stoichiometric coefficients, capital A is the what do you call molecule or what is the reactant. Here A is the reactant, B is the reactant. At time t is equal to 0 before the reaction, let Na not be the number of moles of A, Nb not be the number of moles of B, like that still whatever thing. Nr naught is the number of moles of R, Ns naught is the number of moles of product one more, and some inerts are present. Initially, Nr naught, Ns naught, or if any product is there, it will be 0 because there is no product which is formed at time t is equal to 0. Now at time t is equal to some t, A is being consumed and B is also consumed, R is being formed, S also being formed, and if any inert are there, they are not taking part in the reaction. So at any t, after some time, the reaction happens. How much of Na is present? That is number of moles of A present is nothing but Na is Na naught. That is nothing but number of moles initially minus A times A is nothing but the stoichiometric coefficient. X is nothing but the conversion. So A times conversion minus Na naught will give you how many number of moles is present at a time t. Any doubt here? You want me to write it or it is okay? Any feedback? Ma? Is it okay or you want me to write it? Someone? No one is listening?
Fine, sir.
No one is listening, I think. Okay, fine. So you are writing this much is the reacted. So this much is the reacted. How much is left over is nothing but initial minus how much is the reacted. AX is the reacted. How much it is being reacted, right? So Na is Na naught minus Ax, like that B is Nb naught minus Bx. Nr will be how much is the initial plus how much is the formed plus Rx, like that you have As also. That is the inert. Again, inert is not taking part in the reaction. Any doubt here? So why I'm putting minus here? Because it is the reactant, it is being disappeared. I'm putting positive because the product is being formed. So a product after some time will be much more than the initial. That is why you are getting plus here. The reactant at initial will be less than the will be more than that of Na. That is why you are getting minus here because it is getting reacted. It is being formed. Any doubt in these two steps? Once you write the two steps, then we can calculate the total number of moles at time t is equal to 0 is nothing but this plus this plus this plus this everything, right? Total number of moles initially present. So that is what I am doing. N naught, let it be the total initially the total number of moles present in the system is N naught is Na naught, Nb naught, like that. Anything you are there, Nr naught, Ns naught, plus some inerts are present. Now at time t is equal to 0, again you add all this. Let it be N. N naught, generally not refers initially, right? Suffix not refers initially. This suffix tells you what is the compound which is taking part in the reaction. Okay. So N, let it be N after some time t. Again, this is nothing but if you add all this again, Na naught, Nb naught, Nr naught, Ns naught, that is nothing but plus inerts is nothing but N naught, plus you are adding all the second terms. So x is common, x into r plus s, and if at all anything is there, minus a minus b, that's all is still there. So product, the stoichiometric coefficient, sum of the stoichiometric coefficient of the product minus the sum of the stoichiometric coefficient of the reactants. Is it correct? Now n is equal to n naught plus x into, let this be delta m. That is the sum of the coefficient of the product minus the sum of the coefficients of the stoichiometric coefficients of the reactant. Let it be delta m. So x into delta m, where delta n is r plus s, all this. Right. Now, if you assume the gas is ideal, then we can write Pa. That is, concentration of A is partial pressure of A divided by RT. Or you can write Na by V also. Ca you can write either in terms of pressures or NAs. If you are writing in terms of Na, what is Na? Na already we wrote as Na naught minus A into X. That is what we saw here. Na is Na naught minus A into X. Ax is nothing but how much it is reacted. Na naught is the initial. Therefore, the number of moles present after time t is initial minus how much is reacted will give you that. That is what you put here. So Ca is Na naught by V. So if I divide this Na naught by V minus A by V into delta X. Correct? A by V into delta X. What is X? Now you see Na naught by V. I'm just splitting this. I'm just splitting this. And if I am writing delta N is this. Right? Delta N is this. V I am writing like that. I can write this particular thing. A is common here. X is nothing but if I write X is equal to N minus N naught divided by delta N. From this expression, I can write X. X is nothing but N minus N naught by delta N. That is what I am writing. A by V into X is nothing but N minus N naught by delta N. If I can write like this, now Pa is nothing but Ca into RT, partial pressure, concentration into RT is nothing but Na naught by V. Na naught by V is this particular thing, Pa naught. Pa naught is the partial pressure because you are writing in terms of concentrations, and if you multiply R into T, then you get partial pressure of initial partial pressure minus A by delta N into N by V minus N naught by V. Let N by V is pi minus pi naught. Pi is the pressure. After some time, pi naught is the initial pressure. Right? So this is a very important relation where you are writing the partial pressure in terms of the pressures. Right? So equation 5 gives the concentration or partial pressure of the reactant as a function of total pressure pi at time t, initial partial pressure A, Pa naught, and initial total pressure of the system pi naught. This is a very important relations. What is Pa naught, what is pi, and what is pi naught? PA is the partial pressure finally is initial partial pressure PA naught. That is what initial partial pressure of only A. The A can have that is the reactant can have n number of mixture. B also is there, but here you are writing only for A. PA is PA naught minus A by delta N. A is nothing but the stoichiometric coefficient. Delta N is nothing but the sum of what is delta N? Yeah, the sum of the stoichiometric coefficients of the product minus the sum of the stoichiometric coefficient of the reactant into pi minus pi naught. This is very important. What is pi? Pi is the total pressure of total pressure at time t. Total pressure, the total pressure comes not only from A, even from B, or even from C, whatever may be the reactants, minus pi naught is nothing but the initial total pressure of the system. The initial, that is at time t is equal to 0. What is the pressure? At time t is equal to t, what is the total pressure? This total pressure includes all the molecules, the pressure exerted by all the molecules, whereas PA naught is only the pressure exerted by A alone. Like that you can write for product also. PA, like that you can write for PB also. PB is PBRT, CBRT, PB naught minus B divided by delta N into pi minus pi naught. Like that you can write for product also. PR, that is pressure of the react product. CR dt. PR naught is nothing but the initial partial pressure of R. Is generally this will be 0, right? So still to write to make the comparison, we write this. Here you get negative because the this is for reactant. For a product you add, because this initially it will be 0. So R divided by delta N. R is nothing but the stoichiometric coefficient of the reactant R minus pi naught. These two relations are very important, one for the reactant and one for the product. These two are the desired relationships between the total pressure of the system, and the partial pressure of the reacting systems. This is the total pressure and this is the partial pressure of the reacting system. These two are very important. Please remember, because in the exam they'll give you gas phase reactions. Then you have to write the rate in terms of partial pressures. If you are writing in terms of partial pressures, then to calculate the total pressure, you need to have this particular relation. It's a very important relation. We'll do some problems when we do that problem. I think maybe around some 2 classes. After 2 classes only we will do the problem, because too many derivations will come. That derivations let us do, and then we'll come back to the problems. That time, what is each step, you'll understand much better, because when we do the problem, then we will understand much about this each and every what do you call a term in it. Okay. Any doubt here? Yeah. You want me to do on the now board? I can do, but the time you have to see the time, because too many derivations will come now. Yeah. This is a simple derivation. Here one important thing is writing this particular thing. What is left after time t is nothing but what is initially minus how much is the reactant. Here how much is finally is nothing but how much is initial plus how much is the react, how much is formed. This is reacted, this is formed, plus you put it is formed. Okay. Once you write, then you write the total number of moles for both, and then do the division and all to get in terms of total pressure and partial pressure. This is only for a gas phase. For a liquid phase, we write only concentration. We write only this expression. Only for gas phase, this particular thing will come into picture. Yeah. Any doubt? Shall we go for the next thing? Any doubt?
No, sir.
Yeah, shall I go for the next derivation? Now, since we got, again, we'll go back to the presentation now. In this presentation, I didn't include that. Yeah. So this we already done. Yeah, this in the last class we are discussing about this minus RA, how to, because it's an integral, so it is always better to draw the graphs and then find the area under the curve to give you the entire minus 1 by RA, right? When we do the problem, we'll understand much better. From this, we can calculate the area under the curve is tau by CA naught. CA naught is already we know. Then we can calculate what is the time required for a particular. Yeah, please, 1 second. It is asking me to hold for some time. Maybe some network issue. You are there with me? Some some network issue. Sorry for it. Is it okay, ma? You are there with me?
Yes, sir.
Yes, sir.
Okay, fine. So we'll see here how to do, once we do an experiment in the batch reactor, we get the data, that is the concentration versus the time data we get. How we can process the data? How we can process the data? There are two ways you do it. In fact, a lot of methods are there. One is integral method. The other one is differential method. The third one is initial rate method. The another method is half-life method. And the last one is Ostwald's method. These 5 methods are very important. Some 2 marks question can come. What is the difference between integral method and a differential method? This half-life method is a 2 marks question. What is a half-life method? Or initial rate method also is a 2 marks question. But out of these 5 methods, generally people go for integral method and differential method. What we do, what we are seeing in the last class, especially integrating that particular thing, is the integral method. Generally, integral method we will do, but if the integral method is becoming difficult, then we can go for a differential method. So what is both, we'll see, right? So what is the difference between this integral and differential method? Integral method can be used for a simple rate expressions like minus RA is K into CA. That is first order or a second order. Simple rate expressions, you can use the integral method. This method is used to test a particular mechanism only. Once you have the mechanism, you are getting the rate expression, then only you can use here. But differential method, we can use for a complicated systems, especially if there is minus RA is K times, if you're, I'll just write here, this particular thing is minus RA is K times CA or K times CA square. That's all. Even cube, it becomes difficult, especially integral method. But if there is a minus RA is equal to K times CA power cube or even 3.5 or something like that, very complicated thing, then we can go for the differential method, right? So here we will build the rate expression. Here important thing is in differential method, we'll build the rate expression, whereas we'll test the mechanism here. So how to do, we already saw minus RA is minus 1 by V into dNA by dt is equal to what is that, K into Ca. This is the expression. If you are assuming it is first order, then V is volume constant. So if I take this inside, then I get minus dCA by dt is equal to K times Ca power 1 if it is a first order reaction. Then Ca you get this side, dt you get this side. Then we can write minus dCA by dt or Ca is equal to K into dt. Then you go for integrating both sides to give you the expression, which we saw in the previous class. That is all integral method of analysis. That is, you are assuming some rate, you are assuming some order, and then trying to fit your model with this particular rate expression. But in differential method, what you do is you you won't fix the exit, you write as CA power n. That is some order. N can be any order. And then start doing it, differentiating it, then you get it, right? We'll see that how to do that. So first we'll see the integral method. Integral method is always simple, but differential method is a bit complicated because you are having a differential here. So since you are integrating the differentials, it becomes easy. In differential method, you won't integrate it, right? You are leaving the differentials just like that. dCA by dt is nothing but the slope. So you draw a curve with the CA versus T and then try to find out the slope at different points. Then you get dCA by dt. So you know how difficult it is to draw the slopes. That is why they call it as method of tangents this. So for every point you will draw a tangent, whereas here you just find out the area on the curve to give you the integrals, right? We'll see that. So first, already this we derived in the previous class. I'll just go through it. A constant density, especially for a liquid phase reactions, your minus Ri in terms of any component. I is any component. It can be A, it can be B, or whatever it is. Ri is you're writing for a formation 1 by V into dNi by dt. Constant volume Ni by V becomes Ci, dCi by dt. For ideal gas, Ca you can write as P by RT, that is nothing but N by V. So if I substitute P as Pi and Ri as Ri by because Ca is nothing but Pi by RT. RT is common because it is no constant, so I can take outside the differential. So Ri is 1 by RT dPi by dt. This is a very important expression if you are writing in terms of partial pressures. This is in terms of what you call concentrations. Okay. So this already we saw. We already this is what I wrote. Na minus Na is Na naught minus Na naught into Xa. That is what initially is how much is reacted plus how much is unreacted. If you want to write the material balance, how much A is initially is nothing but how much A is reacted plus how much A is unreacted. You want unreacted. Unreacted is nothing but A initially minus A reacted. So how much is unreacted Na? How much is left over? Is Na naught is initially. How much is reacted is nothing but Na naught Xa. That is what I just put in that previous what you call derivation. Na naught Xa will give you the number of A reacted. Xa is the conversion. Xa is the number of moles of A reacted by initial number of moles of A. That is nothing but the conversion. So Na is Na naught into 1 minus 6A. We can write Ca is Na by V. Therefore, Na naught into 1 minus 6A by V, because you are writing Na is Na naught into 1 minus 6A. So if you are assuming it is constant volume, V is V naught. Na naught by V naught becomes Ca naught, then 1 minus 6A. So you can write Ca as Ca naught into 1 minus 6A. Earlier I am writing like this. This is the derivation for it. Okay. Next thing is what is this integral method, right? I told you there are two methods. One is integral and differential. So in integral method of analysis, we assume the rate expression. Rate expression is minus Ra is minus dCA by dt is equal to K into function of C. This K into function of C can be minus Ra is minus dCA by dt is K into some Ca power 1 or 2 or 3 or whatever it is. That is why I am writing as a function of C. Some power, that is some order, right? So what we do is we rearrange this form, all C to, all concentrations to one term and dt to one side. That is what I am doing here. Minus dCA by function of concentration function is K into dt. So if you put in terms of integrals, then at time t is equal to 0, your concentration is Ca naught. At time t is equal to t, concentration is Ca. So minus Ca naught to Ca, dCA by concentration function is K into dt. Then you do the integral. So once you do the integral, that integral you put on the y-axis, t on the x-axis. you try to find out, because you are having some concentration versus time data. So you calculate this, and then this with this, you plot on a graph. So these are the points, these are the points. And if it forms a straight line, then the slope will give you K. Slope will give you K into T. This is on the Y axis. And if you do this, K into T, right? So this is M and this is X. So you're drawing a graph between Y is equal to MX. Y is equal to MX is nothing but a straight line passing through the origin. X is T, Y is nothing but this. So you get a straight line, then the slope will give you K. That is what you can substitute here. So what you do in the integral method of analysis is you try to find out this and try to find out this and draw a curve, draw a graph, and if you can draw a straight line with all the points, then whatever you assume the mechanism is correct. That is, if you are assuming it is 1 and then do it, then if you are putting that on here and then do it, if you get a straight line, then what you assume the order is correct. If you are getting points like this, like this, like this, then it is not forming a straight line. You are getting a curve. That means that your assumed order is wrong. Then you can assume again minus RA is minus dCA by dt is equal to K into CA square. So you go for the next order, again do the derivation, integration for this, then the integration component into T, again you draw the curve, and if you are getting a straight line, then till you get a straight line, you go on continuing it. That is what is called as the integral method of analysis. So again, you see the plot of the integral of the equation against time. The plot should yield you a straight line with a slope equal to K, because this is in the form of Y is equal to MX. Therefore, M is the slope and the line passing through the origin. If the above plots yield a straight line passing through the origin, then the assumed rate equation is correct. Assumed rate equation, you can assume whatever order you want. If it is 1, then you have to do the integral this and then calculate this. If it is not, then the assumed rate expression is incorrect and another rate expression will be tried. So before doing the integral method of analysis, what you have to assume is you have to assume an order and then do this. This is how integral method will work. Whereas differential method of analysis, no need for you to assume the order. You can put n and then start doing. That is what I'll just show. This will come back again. Will come back again. I'm just trying to show you the. Yeah, this is the. For a differential method of analysis, again we assume the rate expression minus RA is minus dCA by dt is K into a function of C. Plot a graph between concentration versus time. So here in your previous case, you put the C here and then take all the concentration to one term, time to one more time, and then you integrate it. But what you do here is you draw a concentration versus time curve, because you know the concentration with the time. You'll do an experiment. Then that concentration time curve will go like this, because concentration will go on decreasing with the time. So this is a curve you get at different points of curve. You draw a tangent. You draw a tangent at different points. Then this tangent slope will give you minus dCA by dt, because y-axis is CA. The change in CA divided by change in dt is nothing but the slope. So calculate different slopes and then you do this. That is what we do here. Plot a graph of concentration versus time. This is the experimental studies. Draw a smooth curve passing through this origin. It will never be straight line like this, because you get a curve. Then determine the slope of this curve by drawing tangents to the curve at a suitably selected concentration values. What concentration values you want to select, that's up to you. You put it like this at this particular points, you draw a tangent and then find out the slope. That will give you different minus dCA by dTs. So evaluate a function of C at each of these respective concentrations. You can calculate the concentrations at this particular point on the reading on the y-axis. Then plot a graph of dCA by dt. Now you are getting different dCA by dt's. Again you plot a graph of minus dCA by dt versus time versus a function of C to give you a straight line. This, if you are getting a straight line, then this will give you the K. This will give you the K. That is what this. Plot a graph. If we get a straight line passing through the origin, then the rate equation is consistent with the data. Otherwise, if we are not getting a straight line, then another equation to be tested. So in the integral method of analysis, you are doing the rate expression, you are integrating the rate expression. Whereas in differential method of analysis, you are not doing any integral, you are calculating the differential by using the slopes, by the tangents. This is what the method, I'll just show you. This is the concentration versus time graph. You are selecting some different concentrations. At that particular thing, you are drawing a tangents. Again, drawing the tangents is very difficult because you know what is a tangent. Tangent means it should cut the curve at only one point. That is why this differential method of analysis is very tricky. That is why it is complicated, they call. So CA versus time. Once you get this different concentrations or different slopes, you are drawing minus RA. This is minus dCA by dt versus whatever is the function of CA. If you are getting a straight line passing through the horizon, then the delta falls all on a straight line. What rate expression you guessed is correct. Otherwise, you have to test one more expression. This is how the differential method of analysis will go. We'll see this differential method of analysis a bit later. So now I think you know what is the difference between integral method and differential method. Generally, we go a differential method. If we are not getting by differential method, then we will go for differential method, right? So we'll see that now. Any doubt, ma? I will again go back to the previous slides. Now you will much understand what is these two methods. Yeah, now we see the difference now. This method is easy to use and is recommended when testing a specific mechanism, especially a relatively simple rate expression. So in the integral method of analysis, you are separating in terms of all the like terms to one side and all the unlike terms to one side, and then doing the integrals. Whereas in differential method of analysis, this method is useful in more complicated situations, but requires more accurate or large amounts of data, because you need to have different CA versus time, that is different concentration versus time data, because you want to draw a graph, then you have to have large number of graphs, large number of points. This method is used to test a particular mechanism. So what you do here is you try to first fix the order and then go with this, whereas here is not like that. This method is used to develop or build a rate expression to test the data. So if the data is consistent with the whatever assumed expression, you are going to use it. Otherwise, you'll test one more mechanism. Yeah, any doubt with the integral and differential method of analysis? Am I going a bit fast or slow, or yeah, some feedback? You want me to go slow? I will go a bit slow. Yeah. Any feedback from this? You want me to repeat, or shall I go for the integral method? Now we'll see the integral method first. Yeah, any doubt, ma? Yeah, some feedback please give so that we'll go move forward. Guru Prakash, I think now 60 people are there. Please take the attendance now. I don't think more than that it will come. 60 people, so more 5 people, 6 people will be absent, I think. 60 includes me, I think. Yeah, any doubt here, Guru Prakash or Yamini? Yamini, any doubt, ma? Girls side?
No doubt, sir.
You understood now what is differential method and integral method? You want me to repeat? I'll repeat.
Yes, sir. Understood.
So we'll move ahead because we'll be seeing the integral method. You will understand much better when what is this integral method when we are using. Okay. Differential method will take a bit later because in integral method there are a lot of reactions, different types of reactions. First we'll go with this method. Let us go for integrated approach to different orders of a reaction. So let us first topic is please take a notes. Please do simultaneously along with me because if you are seeing the PPT, you won't get it. Again, I'm telling you, it is very difficult to follow. Take a notes, start writing whatever is there on this particular thing. You do the integral. Yeah, please all of you take the notes. I'll do it. At least for one or two, I'll do it. Rest of the thing, once you are in that group, then we can skip it. Okay. Let us do it now. Consider a reaction. A is giving you product. So I am taking some A is giving you some product which is having some K. All of you are having notebook with you? Yeah. Guru? Guru Prakash, you're there?
Yes, sir. Yes, sir.
Yeah, please take a notebook. Dimple, you're there?
Yes, sir.
Yeah, please take a notes, all of you. Start writing with me. I'll write so that if you are not writing, you won't get it. It looks like some other thing. This becomes that, that becomes this. Let us do derive it. Then we will understand how it is being changed. Right? Please, all of you take your notebook. Do along with me. Yeah, I am taking A is giving you some product. So let me use some other pencil here. Let me use some other, yeah, I'm using some other color so that it will be easily to identify what.
I thought everybody said I loved Aria. I loved his
Minus
transformation.
RA is, I'm writing for this, minus DCA, yeah, please mute yourself. DT is equal to K into CA. We are assuming it is unimolecular because you are assuming it is unimolecular. That means only one molecule of A is there. And the order is first order. So N, Ca power N, N is nothing but 1, right? So we are doing an integral method approach. So what we have to do? Minus Ra is minus dCA by dt is equal to K into Ca power 1. Let it be first order. So what is the next step I have to do in this? Get all the Ca terms to one side, take all the T terms to another side, right? So let it be this particular thing, minus dCA by Ca is equal to K into dt. Is it correct? I'm just equating these two because Ra is this or Ra is this. I'm just equating these two. So this is the form, all the Ca terms to one side, all the dt terms to one side. So we done second step. So next step is to integrate this. K is a constant, therefore you are integrating here 0 to t. When t time, because you are integrating with the time, when time is 0, your concentration is Ca naught. When time is t, your concentration is Ca. So integral of minus dCA by Ca. You know that integral of 1 by x dx, integral of dx by x, integral of dx by x is nothing but log x, right? Integrations, right? So this is nothing but ln, minus is there, minus ln Ca, and then you have to substitute the limits. So you get minus ln Ca by Ca naught, correct? Correct. Because this is dx by x, therefore log x you get. So ln Ca, if you substitute the limit Ca by Ca naught, this minus will remain. That is equal to K into T. Because dt is T, if you substitute lower limit and upper limit minus lower limit, you get T. So if you take this plus inside, then what will happen? This becomes Ca naught and this becomes CA, right? CA naught by CA. So you want time. Generally, we want time. T is equal to 1 by K. Sorry. Yeah, 1 by K into ln CA naught by CA. This is one expression if you want time. Otherwise, you want some, what is K? K is nothing but 1 by T ln CA naught by CA. Sorry. Yeah, ln naught by C. Either you can find out the time required for a concentration, whatever concentration you want, or if you want to have what is the rate constant, if you know the time at a particular time, because rate constant is going to be constant, right? You can find out this. This expression of calculating the rate constant is only for unimolecular first order time. So now draw a graph between ln CA by CA naught, ln CA by CA naught, and then versus time. That is what I'm doing. ln CA by CA naught versus time. Then you get a straight line. Then the slope will give you K. This is what is the integral method of analysis. You can go with in terms of concentrations. You can go with the conversions also. This is nothing but CA is CA naught into 1 minus XA. So all the CA terms to one side, all the DT terms to one side. If you put it, then you get dXA by 1 minus XA is K into DT. Again, you integrate between the limits of 0 to T. Where time 0, your conversion is 0. At time T, your conversion is XA. Then if you're doing this, dx by minus x is nothing but minus ln x. That is what minus ln x, one more thing. Because here minus is there, your minus is not there. You put a minus here, then minus, then this is in the form of dx by x. The integral of it is ln x. This minus will remain here, is equal to kt. So this also you can do, this on the y-axis, this on the x-axis. The slope will give you k. That is what is minus ln 1 minus xa or minus ln ca by ca naught is, you can put whatever on the y-axis. Therefore, t, you try to draw a graph, and if all the points fall in a straight line, then the slope will give you k. If you are not having in the points, then what you do? You assume it is a first order. So let us assume it is a second order, and then repeat the process. If you are getting a straight line, then you can get it is second order. That is CA square or CA power 1. If it is a straight line, you are getting 1. Otherwise, you go for one more order. That's how you have to do. For every thing case, this y-axis will be different. So let us do one more expression now. Any doubt, my here? First order. Yeah, please give the feedback. Some people. Divya Darshini, you are there. Divya Darshini.
Yes, sir.
Any doubt, ma? You are
No,
getting
sir.
in terms of conversion and concentration both.
Yes.
So if your order is increased, this integral becomes difficult to do. It's not that easy. Now we'll do with one important thing is half-life. What is the characteristics of first order kinetics is the half-life. What is half-life? This is a school chemistry. The time required to reduce the concentration of the reactant to half of its original volume. So half of its original volume, in the sense you are getting for a first order thing, what is the expression? K is equal to 1 by T ln Ca naught by Ca, correct? This is the expression for a first order. So ln you can convert to log also. K is equal to 2, if you want to write T, because time is because half-life period we want. Time is nothing but 1 by K. ln if you convert to log, it is nothing but 2.303 log Ca naught by Ca, right? This is the natural log and conversion base 10 and base E. So now if you convert the limits, T becomes T half a T becomes T half, your Ca becomes Ca naught by 2. That is what we want, correct? The final concentration half-life period is nothing but reducing the concentration of the reactant to half of its original volume. This is the original volume, by half of it is Ca. So if you substitute both here, then what will happen? T is nothing but T half, that is 2.303 divided by K into log Ca naught is nothing but Ca naught divided by Ca is Ca naught by 2. Ca naught by 2. This is the entire bracket. Ca naught get cancels. 1 by 1 by 2 is nothing but log 2. T half is nothing but 2303 divided by K log 2. Right? Log 2 you get. So log 2 into this, if you multiply, then T half is nothing but this particular expression. So once you know the rate constant, you can find out your T half of that reaction. That is how much time is required for the reaction to reduce half of its original volume by using this expression. This expression, I think you already in your higher school chemistry, you might have studied about this. This is the what do you call derivation for it. This derivation also you might have got. You don't know how you are getting that. This expression. They just uses the expression and then in the expression they substitute the limits. Now we came to know how we are getting this expression. This is holds only for a first order kinetics. If there is a second order, this will be different. We'll see that. Any doubt, my here?
No, sir.
Based on this, they will ask some 2 marks question. Calculate the T half, that is half-life period of a reaction, which having the rate constant as. They'll give you the rate constant, and then they will ask. Rate constant will have a unit K. You will have a unit of per second. So 1 by second. So T half will have a unit of seconds or hours or whatever it is. Okay. So now let us use the bimolecular. Now, if there is an equation called 2A gives product or A plus B gives product. 2A gives a product, it is a bimolecular, but a second order reaction. Your second order can have 2 reactants, A and B, both is having first order. So overall order also becomes 2. So these 2 types of reactions we have to do by differential method, integral method of analysis. I don't think I will have a time now. Just will do with 2A gives product is a bimolecular. So you are writing minus RA is minus 1 by dCA by dt is K into Ca square. Earlier you are writing Ca power 1 because you are assuming it is first order. Here you are assuming it is second order. That is why Ca square you are getting. So if you make all the Ca terms to one side and dt times to one side, minus dCA by Ca square is K into dt. Correct. So now here again some integration of dx by x is nothing but ln x. Integral of dx by x square is nothing but 1 by x. Plus c will be there constant because integration constants will come, right? That you substitute the limits and then find out that, right? So any doubt in this? So no need for me to do this integral, right? You can get this minus 2. Then if you want to integrate integral of x power minus 2 dx is nothing but x power minus 2 plus 1 divided by minus 2 plus 1. So this is nothing but minus, this is nothing but minus 1, therefore 1 by minus x. That is what you get, right? So this is all some basic integration thing. So here it is x square is there. So integral of this entire thing, integral of this is 0 to t and this is Ca naught to Ca. The integral of this is nothing but minus 1 by x. Already there is one minus. So minus into minus becomes plus. That is what you are writing. This is minus 1 by Ca. Minus 1 by Ca. Integral Ca naught to Ca. This is what, right? Yeah, CA to CA naught at time t is equal to 0. CA to CA at time t. These are the two limits. If you substitute the limits of this is minus 1 by CA. This positive, I think it will be, because here already one negative is there. Here one more negative will come. Therefore, minus into minus becomes positive. If you substitute the limits 1 by CA naught, 1 by CA, because upper limit minus lower limit. Correct. This is positive. Sorry. There is some in the notes it is positive. I put as negative. So we want K. K is 1 by T into CA naught minus CA. This is for second order bimolecular type, right? Bimolecular. What is for the your first order? You are getting as K is 1 by T into, yeah, previous thing you see. Yeah, CA naught by CA you are getting for the first order. But you see as the order increases, you are adding some extra terms here. This is in terms of conversion. You can put in terms of concentration, or this is in terms of concentration. You can put in terms of conversion also. That is what here I am showing. In a conversion, you are writing CA. You know that CA is CA naught into 1 minus XA. So CA square is CA naught square 1 minus XA whole square. That is what we put here. CA is CA naught into 1 minus XA divided by CA square is nothing but CA naught XA square. K into dt you put this. Correct. So CA naught is common. You take it out. Here differential of A into B. CA naught is going to be common. You take it out. So CA naught divided by CA naught square. So 1 square will get cancelled out. So 1 CA naught will be there. That CA naught you get this side. K CA naught into dt. So what is left inside? Differential of 1 minus XA divided by 1 minus XA whole square. This negative, therefore positive. So dXA by 1 minus XA whole square is equal to K into CA naught into dt. This is the expression which you are getting. Now you integrate the limits. So K is constant, CA naught is constant. Integrate between the limits 0 to t. Again here integral in between the limits, when there is a time 0, your conversion is 0. When conversion time is t, let the conversion is XA. So if you substitute the limits, again here it is same. 1 by XA square is minus 1 by x. That is what you are doing. You are using 1 minus XA as y. Then this comes as dx is equal to dy. So you do that, final form of the equation will be like this. This is for the second order bimolecular type. If it is a unimolecular, Kt is minus ln 1 minus Xa. This is for the unimolecular first order reaction, whereas this is for the unimolecular, bimolecular second order reaction, Xa by 1 minus Xa. So if it is third order, again still one more term will come, because this will be cube here. Then this becomes cube. This becomes square. Ca naught a square will be coming. This will become cube. Then it's not that easy to do that. Understand? So that is why integral method of analysis fails when you are getting some higher order. Right? I'll stop here. I think time is up. You understood how to do? Any doubt, ma? Yeah. Please give some feedback. Nishant, you are there, ma? Nishant?
Yes, sir.
Any doubt, ma?
No, sir.
Please do in your notebooks, then you will understand. Right? So I'm going slowly only, because too many derivations will come. It's not that easy to do all that on the board, because you have to see the time also. Simultaneously, I require your cooperation also. You have to do in your notebook, and if any doubt getting the final expression, yeah, just tell your thing, then I will solve that. Okay. I'll stop here. I think please do it in your notebook. Still 2 more days is there, Wednesday. So if any doubts you are having, I'll clear on Wednesday. Okay. With that, I'll stop here. I stop the recording and